We have now looked at the Bohr model and at how that causes atomic spectra, or how we can use it to explain, rather, atomic spectra. So I want to do an example with this. So this is sort of atomic spectra as an example, or maybe just energy transition levels. Let's say I have, we'll do a simple one first. Let's say I have hydrogen, and I am looking at an electron in the n equals 1 level. It's going to excite to n equals 4, then drop to n equals 3, then n equals 1. And I want to find the wavelength of each photon. What I know right away, this is hydrogen, so I know I'm looking at a Z of 1. I would like to say my energy levels are negative 13.6 eV times Z squared over N squared. I'm going to need the N equals 1 level, 3 level, and 4 level, so I'm just going to calculate those. Alright, I've got those energy levels. I'm first jumping from n equals 1 to n equals 4. Then I'm going to jump from 4 to 3. And then from 3 back down to 1. So I've got 1, 2, 3. Process 1, I am absorbing a photon. And the photon that I'm absorbing is going to be the difference between those. So I'm going to get a negative 13.6 eV minus a negative 0.85 eV equals 12.75 eV, because I stuck it in absolute values. The energy of my photon is equal to hc over lambda. And that means that my wavelength is equal to hc over the energy. H times c is 1240 EVNM. That was my shortcut from before, over 12.75 EV, and that works out to be 97.25. So we'll say 97.3 nanometers. That's my first photon that I'm going to have to absorb. Now I'm going to look at the emission of a photon. So I'm going to have to emit a photon. My energy of the photon is going to go from 4 to 3. So I'm going to have a negative 1.51 EV minus a negative 0.85 EV. By sticking these things in absolute value, I don't have to worry about the order of them at all. and I get 0.66 eV. And then my wavelength is going to be 1240 electron volt nanometers over 0.66 eV, and that gives me 1880 nanometers. This one, 97.3, this is too small of a wavelength for me to see. This is too high energy, so this is not visible. Because it's too far ultraviolet. This one's not visible because it's too far in the opposite direction. And now we'll look at the last one. 3:1. We are again going to emit a photon. We were in the n equals 3 level. We need to get to the n equals 1 level, so we need to drop. So I'm going to go 13.6 eV negative minus negative 1.51 eV, and that's going to give me 12.09 eV. My wavelength is 1240 electron volt nanometers over 12.09 electron volts, and that gives me 103 nanometers, which is again not visible because I am too far ultraviolet. I want to do a different example, and I want to look at positive helium. So helium has an atomic charge of 2, meaning helium plus is down to 1 electron. This should behave reasonably closely to my expectations from the Bohr model. And I happen to know that for singly ionized helium, I do get a wavelength, a photon wavelength, a spectral line of 468.9 nanometers is one of my wavelengths. I would like to find what transition that is. 468.9 puts me in the blue range, so this is one that's visible. So now I want to try this. I'm going to just write out some of my energy levels. Let's see where this lands. So I want to find my photon energy first, and I'm going to continue to use this 1240 eV nanometers because it is really convenient anytime that we have visible light given, especially that frequency, or that wavelength rather, tends to be given in electron volts. So it's, anytime we have a photon that's visible, the wavelength tends to be given in nanometers. So being able to take this shortcut is a really nice deal. But this comes out to be 2.64 eV. So now I want to compare that to some of these differences. I'm going to ballpark figure these first, and then I'll try and fine tune as I go. So 54 minus 14, that's something like 40 eV. That's too much. If I go 54 farther down, it's going to be worse. So I can pretty safely say it's not this. 13.6 down to 6, so 13 minus 6, that's 7. And again, too high, and it's only going to get higher. I don't like that one. 6 minus 3.5, well 6 minus 3.4, that's about 2.6. This looks like what I'm looking for. So let's try it. We're going to say 6.04 EV minus 3.40 EV in the absolute value gives me a 2.56. Sorry, gives me a 2.64 EV, and that is the one I'm looking for. This photon that I'm seeing must be from my n equals 4 to n equals 3 transition if it's an emission, or 3 to 4 if it's an absorption. That's how I would do these problems.